Hello, this is Dr. Vladimir Goncharov bringing you lecture for Wednesday, April 23rd, the second lecture of week 14 in the spring semester. On this day, we're having a makeup exam, so obviously this video lecture material will not be covered on that exam. This lecture introduces you to the Laplace transform, and of course, all of you have seen it before in differential equations, because the Laplace transform is very useful at solving differential equations using algebra. We'll talk about the bilateral and unilateral forms of that integral, the region of convergence for this transform, and then properties and transform pairs just as we had for the Fourier transform. There's also one more topic that I forgot to put in this list, and that's the very last topic of the lecture. I'll show you some examples of analyzing circuits using the Laplace transform. Recall the Fourier transform. F of omega is the integral over all time of the product f of t and e to the minus j omega t. The Laplace transform may be thought of as a generalization of the Fourier transform. Take j omega in the exponent and convert this purely imaginary constant product to sigma plus j omega, thus giving it a real part, making it complex. There it is. And if we take that exponent, split it up into two parts, and associate e to the minus sigma t with f of t, we see that what we've done has been to redefine the function of time that we are Fourier transforming. Instead of f of t, now it's f of t multiplied by some normally decaying exponential, and it makes possible that some f of t's that were not Fourier transformable as a result of this operation become Fourier transformable. But there's a better way of looking at the Laplace transform. The Laplace transform, instead of being looked at as a redefinition of f of t, the function of time, we will redefine the Fourier transform instead. That e to the minus j omega t now becomes e to the minus st, where s includes real and imaginary components, and this then is called the Laplace transform. The Laplace transform is a generalization because, as we will see, now this function of s, where s is complex, contains as a subset the Fourier transform, but also expands the region into the entire S-plane where the transform may be evaluated. The bilateral Laplace transform is the one that was just mentioned. It has a region of integration, looking at the time scale of this integral, spanning from minus infinity to plus infinity. Both sides of 0 are included in the integral, hence it's called bilateral. The unilateral transform takes only 0 and to the right of it, so that impulses that occur at 0 may be included in the integral. We actually define it as 0 minus to infinity, and this means that causal signals f of t will have the same unilateral transform as they have bilateral transform, because they naturally are 0 to the left of 0. So when f of t is causal, there's no difference between these two transforms. The inverse Laplace transform is applied to f of s, the transformed f of t. And it is defined this way. Looks similar to the inverse Fourier transform, except for there's a j in the denominator and a scaling factor. Of course, j omega is changed to sigma plus j omega, or s. And the integral, instead of taking place over all omega, it now takes place for all omega when sigma is held constant for a particular value sigma naught. The thing is, the Laplace transform may not converge everywhere in the S-plane. So sigma naught defines a line in the S-plane where f of s is assumed to have converged. Let's look more at this region of convergence. So the bilateral Laplace and also the unilateral Laplace transforms may not converge for all values of sigma in this expression, if at all they converge. But if it happens to converge at some point s sub 0, as shown here at the bottom, where s0 is defined by its rectangular coordinate sigma 0 plus j omega sub 0, if the integral converges at that point, then it will also be true that the integral converges along a vertical line passing through that point. The line defined by sigma sub 0 plus j omega, where omega is allowed to vary from minus infinity to plus infinity. So this gives us insight into the regions of convergence that may be present. They all will look like vertical stripes that include all values of omega for a particular value of sigma. Here's an example of that. Let's assume that the region of convergence from now on will be abbreviated ROC, is this stripe that is between sigma equal to sigma sigma 1 and sigma equal to sigma sub 2. That shaded area is a region of convergence. So f of s is only defined over that shaded region. For all other parts of the S-plane, the complex S-plane as shown here in terms of its rectangular real and imaginary components, f of s does not exist, has no formulation outside of that shaded region. This is just an example, but it's easy to come up with functions that have this particular region of convergence. And now a specific example. The unit step function may be Laplace transformed using the bilateral Laplace transform. And on the top line, the very right expression, the lower integral limit is changed to 0 because u of t is 0 for all negative time. And the integral then, as shown on the bottom line, is that of a complex exponential. The complex exponential may be separated into two parts, and it turns out that a finite result of this integral is obtained, or one that converges to a fixed finite value, is obtained only when sigma, which defines the first exponential, is greater than 0. Therefore, we say that the Fourier transform of the unit step function, which not proven here, just given, is 1 over s, only exists in the region of convergence of the S-plane where sigma is greater than 0. This is derived on page 6 in Chapter 9 handout. Plotting this in the complex S-plane, we see for the left half S-plane, f of s is not defined, including the j omega axis. The omega axis, the vertical axis, is also outside of the region of convergence. Only for positive non-zero values of sigma is f of s obtained to be 1 over s when solving that integral. So that is a region of convergence of the Laplace transform of the unit step function. It's interesting to note that it's possible to have different expressions, the same expression for f of s for different time signals f of t. The only thing making them different in the S domain is a region of convergence. Here's a specific example of that. A decaying exponential e to the minus sigma t, where sigma is greater than 0, times u of t. It has a Laplace transform 1 over s plus alpha, which is only defined when sigma is greater than minus alpha. Now, if you take another signal, turns out to be minus e to the minus alpha t times a time reversed unit step function, it too has the same formulation for the solution to the integral for f of s, except that that formulation results only when we assume that sigma is less than minus alpha. So we have the same formulation for f of s, but two different time functions. What discriminates them are the regions of convergence. It's worthy of mentioning that the first of these functions was causal, and that led to a region of convergence that was sigma to the right of some value in the plane. And the other one was anti-causal, which led to a region of convergence that was sigma left of some value. This will be the case for every causal and anti-causal signal. The regions of convergence are to the right for causal and to the left for anti-causal of the vertical line defined by some sigma. So restating these two Fourier transforms, we must stress the fact that f of s alone cannot recover f of t, what we start out with in time. We must also know the region of convergence. And when solving the inverse Laplace transform expression, it is a sigma within the region of convergence that is used to perform that contour integration. We can take the easy way out, however. Instead of worrying about the region of convergence all the time, take only causal functions of time, for which, as I mentioned, the region of convergence is over the range of sigmas that exceeds some value. That is kind of a right half plane. Once we limit our scope of functions to be transformed to only causal ones, then all we need to know is f of s and the value of sigma naught that forms a left boundary of the region of convergence. And in most cases, it can be gotten by inspection from f of s itself. So there really will be much less confusion as to what we're talking about in the time domain. So that's why f of t being causal means f of t is equal to f of t times u of t is a subset of all the functions that we will consider, and this is forced by using the unilateral Laplace transform, taking the integral starting at 0, just to the left of 0, 0 minus, up to infinity, which essentially, even if f of t was not causal, will be transforming a causal made function by multiplying it by u of t. So let's take a quick look at Laplace transform pairs that were in the Chapter 9 handout on pages 9 through 10. The left column is a time domain function, the right column is f of s, and the region of convergence is not mentioned. Why? Well, it's because all of these functions are causal. So, as I said previously, we may deduce the region of convergence from f of s. For example, the region of convergence for the delta function, delta of t, is 1 everywhere in the s-plane. Whereas u of t, which has 1 over s, notice that at s equals 0, this thing does not converge. But to the right of sigma equals 0, it does. So that's why the region of convergence is defined by the left edge, sigma is equal to 0. The second entry from the top, e to the minus at u of t, is 1 over a plus s, and that has a region of convergence, sigma greater than minus a. Continuing with more properties, we see that they are very similar to those that we had for the Fourier transform. Except now we have some possibilities that did not exist for the Fourier transform. For example, take a look at fourth from the top, t u of t. This is a ramp function, and it has Fourier Laplace transform 1 over s squared. This did not have a Fourier transform, but over a certain region of convergence, we may think of it as multiplying a ramp by a decaying exponential in order to make the Fourier transform exist. Well, that essentially is a Laplace transform over a specific range of sigma values. And we end with the last few entries in the table 9.1. And let's take a look at the Laplace transform properties as well. These are actually more interesting because now we've gotten used to working with transforms. We know that the properties are very important. For example, the first one, linearity. This is absolutely a must if we are to handle signals adding together before they are applied to a system. So the additive property as well as the superposition property are very important at allowing us to analyze linear systems. Time scaling property, very similar, in fact, easier expression than the Fourier transform version of it. Time delay, notice that a time delay f of t minus t0 results in multiplying the Laplace transform f of s by e to the minus st0, whereas before it was e to the minus j omega t0. So very similar. Because we're dealing with causal signals, we must be careful. For example, f of t times cosine omega naught t. It looks very much like the modulation property that we had for Fourier transform, except keep in mind f of t is causal here. So only half of it is multiplied by the cosine, and to the left of 0, there's a 0 product. Multiplication in time is convolution in frequency. Convolution in time is multiplication in frequency, and so on. So I'd like to make some comments now about the Laplace transform. The Laplace transform is used when we deal with systems. If we're talking about signals only, as we have been through chapter 5, then I believe that the Fourier transform is just as useful. But when you talk about systems, you get much more insight by using Laplace transform. Even though you can think of impulse response h of t as a signal, it actually represents a system behavior. So these benefits, this greater insight, are that we may now perform stability analysis of the system, see if it's on the verge of oscillation, or designing it in such a way so that it does not oscillate or does oscillate. We have much more insight as far as filter design. The notation is less cumbersome because instead of dealing with j omega or e to the j omega all the time, now we're dealing with s. And you'll find that you might not even see a j or an exponential as you did before in much of what we do. For example, h of s for circuits and many other applications is rational. It's a ratio of polynomials in s, making the notation so much easier for us. Now, one more comment. The Laplace transform of f of t has a region of convergence, and if that region of convergence includes the j omega axis, that is, the line defined by sigma equals 0, then the Fourier transform may be evaluated simply by substituting s with j omega in the expression for f of s. So that's why we say that the Laplace transform is a generalization of the Fourier transform. However, if the Fourier transform that we had stretched to its limits by including impulses in order to have the possibility of representing periodic signals or power signals, if that spectrum contains impulses, then the Laplace transform cannot possibly be converging at sigma equals 0. Those impulses are, in fact, non-convergence. So there's no sense to allowing us to use impulses in the S domain. All we do is shift the region of convergence a little bit and we continue working as usual. Therefore, in such case, let's say a cosine wave that goes on indefinitely in both directions from 0, that has impulses at plus minus j omega sub 0. In the S-plane, those, I call them impulses, but they're really non-converging points of that integral. Therefore, you cannot get the Fourier transform from f of s for that function because f of s does not exist there, you see? And this is one of the exceptions to the rule shown above. Now, to finish off this lecture, I'd like to show you some practical uses for the Laplace transform, and this is in circuit analysis. You'll recall we talked about impedances and how the impedance of an inductor may be found by Fourier transforming its voltage-current differential equation relationship. The same thing can be done with a Laplace transform, and now we'll have a statement for impedance in terms of S instead of omega. Instead of j omega L, now we've got SL. For the capacitor, instead of impedance being 1 over j omega C, we now have 1 over SC. Much more convenient. Of course, it should be said that in both cases, the element itself, inductor or capacitor, were assumed to be at 0 initial conditions. The resistor, as before, has impedance R. It is not a function of S. It's a constant. Taking this information, let's find the transfer function, the voltage transfer function for this ladder network, defined as a Laplace transform of V out divided by the Laplace transform of V in, or H of S. Here's how we do it. First, redraw the network, this time with impedance values. And instead of time labels for the signals in and out, put in a Laplace transform version of those time waveforms so that you remind yourself that we are now in the S domain. I've done that here without specifying any particular component values, left them in terms of R, L, and C. Next, use circuit analysis techniques as if these were resistances to calculate the ratio of V out to V in. So we have a series shunt network. We take the impedance of the shunt element, put it on top, and on the bottom put the sum of series and shunt impedances. Notice that the series impedance is R plus SL because they're in series. And then I've simplified it by multiplying top and bottom by S over L and expressed it now as a constant over a second order polynomial in S. S squared plus R over L quantity S plus 1 over LC. This expression, if the denominator is factored under certain conditions, will have complex conjugate roots. That is, values of S in the complex S-plane that cause the denominator to go to 0, which of course makes H of S go to infinity, and therefore these cannot lie within the region of convergence for the Laplace transform of H of t, which is H of S. These typically form a boundary to a region of convergence. The vertical line passing through these complex conjugate poles forms the boundary of the region of convergence. If we take this H of S and replace S with j omega, we now have the frequency transfer function. So much easier dealing with S algebraically than it is with j omega. And therefore, H of S for circuit analysis is used extensively, and H of omega, or H of j omega, as some people say, is rarely used when we deal with circuits. We may make a substitution at the very last step, making S equal j omega in order to get a frequency response, but normally we try to keep that j omega out of the picture as long as possible to simplify the expressions, to make them less cumbersome, to make fewer mistakes. Thank you for your attention. This is the end of video lecture 14-2.